Hi, welcome to the QuickerSim CFD Toolbox for Matlab tutorial number 9. In this tutorial, we will simulate a simplified aerodynamics flow case. Let's have a look at the geometry so that I can give you more explanations. Basically, two squares on the bottom serve as simplified models of buildings, and the flow goes from the left to the right. The ground and the buildings are obviously no-slip walls. The inflow is defined as velocity inlet. The outflow will have zero constant pressure, and the top will have symmetry boundary condition or other set slip boundary condition. Because this will be a turbulent flow, we will also require boundary layer generation. Boundary layers will have to be generated on the no-slip walls. In order to do that, we will be using the function that's called extrude layers to D. Okay, so let's have a look at the modified geometry. Yes, so yeah, you can see that the boundary layer has been generated in here. Okay, you can set lots of extra parameters for boundary layer generation here. 4 layers, the ratio is 1.5 or one layer to another, and the basic height is 0.02 for the lowest step, and those are the wall IDs that are required for boundary layer generation. Okay, then we need to proceed to defining the rest of the simulation. The operating fluid is air with viscosity 1.5 times to 10 minus 5th power. We initialize solution with 0 velocity, set the maximum convergence criterion to 10 to minus 5, 50 iteration steps, and we also use under relaxation parameter alpha equal to 0.6. Finally, because we will be performing turbulence simulations that need some extra parameter in form of the wall distance, that is the distance from a computational cell to the closest wall, we have to store this distance into variable d and calculate that using the function compute wall distance. We also have to store the copy of the velocity pressure variable, so we create variable us that simply equals u. Next, we define the value of the inlet velocity profile, that is only horizontal velocity 0.43 meters per second. Now, let's have a look at our main iterative loop, because that's where most of important things happen. Since that's a turbulent flow simulation, we need the additional variable that's called the turbulent viscosity. We calculate it simply using the function turbulent viscosity with proper arguments. We are using the so-called Srebridge model for turbulence that's particularly suited for aerodynamics. You can find more references in here. That's the whole paper that describes the model. And you can also look for help if you want to find more details how to define the model. So you can see for Srebridge model, two last arguments will be turbulent intensity, which is set to 0.1, as well as the inflow Reynolds number based on the building height. Next, we use the under relaxation to calculate the next step value of velocity by using the previous value of velocity as well as the additional variable us, and we assemble the Navier-Stokes matrix for our calculations using the function that you already know from previous tutorials. Further step is standard. We have to impose the boundary conditions. On the left there is inlet with velocity vel. Also there are walls, no slip boundary walls defined at wall IDs. You will see that wall IDs have already been defined at the very beginning because there are quite a few edges of the ground and its square sides. Finally, at the top edge of the mesh we define the slip. Simply there will be no normal component of velocity over there. At each simulation step, we compute the residuals for our system of equations and plot them. And if the solution is converged, that is the logical value of stop equals 1, the calculations are stopped. Everything is solved using basic Matlab routines. US is copied and U is solved as NS divided by F. When the simulations are completed, we will be able to display the variables that we look for. We will display horizontal velocity component, value of turbulent viscosity, and also the ratio of turbulent viscosity to basic air viscosity. Okay, so let's run the whole simulation. The plot is converging pretty fast. And here you can see the results. First, let's have a look at x velocity. It's obvious that it should be close to 0 at the no-slip walls. You can obviously see the practically dead zones that occur in the vicinity of the squares. You can see the boundary layer here being developed. It seems that there's a strong recirculation zone in the region between two squares because velocity here is in fact negative. And again, the same thing, there's a recirculation zone past the square. Okay, let's have a look at other variables. So that's the turbulence viscosity. So this is extra viscosity that is added to the Navier-Stokes equations. And you see that it's larger in the free stream. But the most important thing is how turbulent viscosity compares to basic viscosity. And you can see that in the free stream part, it is like almost 50,000 times larger than basic air viscosity. But it is much lower in the vicinity of the walls. Okay, that's it for this simulation. Obviously, you can do much more of pre-processing and post-processing that you want. For example, you could plot velocity, integrate pressures, and so on. We hope that you like this exercise. Please visit our website, QuickerSim.com/toolbox, and also go to our YouTube page to check out other tutorials. Thanks for your attention.